Today we're going to be taking a look at ionization energy. So ionization energy is another trend that changes systematically as you move across or down the periodic table. It also is given on reference table S, so we can look it up on table S. So ionization energy is the energy required to remove the most loosely bound electron from an atom. So for example, if we take a look at our first two elements, hydrogen and helium, hydrogen has an ionization energy of 1,312 kilojoules per mole, and helium is 2,372 kilojoules per mole. So that tells us that actually they both require a lot of energy to remove an electron, but the lower the ionization energy is, the less energy is required by another atom to remove that electron. So the more likely that thing is to lose electrons to form positive ions. So that would be our metals. Whereas like helium's ionization energy is very high. So that means that it requires a lot of energy to remove an electron from that atom. So that means that atom is not likely to lose electrons. So it would be much more likely to gain electrons to form negative ions. So that would be a nonmetal. Or in helium's case, it's just going to not gain or lose electrons since it's a noble gas and already has a full valence shell. So the first thing that we are going to look at is the trend across a period. So we are going to look up the ionization energy of potassium. Potassium is at the beginning of period 4, meaning that it has 4 electron shells. So the ionization energy for potassium is 419 kilojoules per mole. The ionization energy for bromine, which is almost at the end of period 4, is 1,140 kilojoules per mole. So we can see that it takes way more energy to remove an electron from the bromine atom than it does for potassium. We also can see that ionization energy would increase as we move across the table, across the period. So as we move across the period, the ionization energy will increase. That is because they will maintain the same number of electron shells. So potassium and bromine both have 4 electron shells, but the number of protons increases. So bromine has more protons than potassium. So therefore, there is a stronger attraction between bromine's nucleus and bromine's electrons. So the nucleus has a better hold or a stronger attraction with the valence electrons. Therefore, more energy would be required to remove an electron. So you can think about it like magnets. If you have 2 strong magnets, it's harder to separate them. It takes more energy to separate them. So the stronger the nucleus is, the better the attraction would be between the nucleus and the valence electrons for things that all have the same number of electron shells. All right, now we are going to talk about what happens as we move down the table. So as we move down a group. So we are going to look at lithium. Lithium is at the top of group 1. And if we look up its ionization energy off of table S, it has an ionization energy of 520 kilojoules per mole. Francium is at the bottom of group 1, and that has an ionization energy of 393 kilojoules per mole. So we can see as we move down the periodic table, the ionization energy decreases, meaning that it becomes easier to remove an electron from francium than it is from lithium. So to summarize, as we move down a group, the ionization energy would decrease. That is because as you move down a group, the number of principal energy levels or electron shells increases. The valence electrons are further away, So the nucleus cannot hold on to those valence electrons as well. Therefore, the nucleus is further from the valence shell. So there is less of an attraction. It's like having magnets be too far apart. There's not going to be good attraction. So this table here just gives us a great visual of our ionization energies. So up in the upper right hand corner, we have very high ionization energies. And then as we get towards the bottom of group 1 and 2, they are much lower. All right, in our first question, we're looking for which one will lose electrons the easiest. So first off, we want a metal. So if we have a non-metal, we can cross that off. So chlorine, fluorine, not going to be good choices. Now we also want something that has a lower ionization energy, because the lower the ionization energy, the easier it is to remove electrons from that atom. So if we look up sodium on table S, we see that has an ionization energy of 496 kilojoules per mole. Potassium is 419 kilojoules per mole. So that means that it takes less energy to take an electron from potassium something's out shopping for an electron, and taking an electron from potassium would cost less than taking it from sodium. All right, then our next question, which is also labeled number 1, what's the ionization energy of potassium? So that is going to be 419 kilojoules per mole. We just did that in the previous problem. And calcium has an ionization energy of 590 kilojoules per mole. All right, they both have 4 electron shells, but potassium has 1 less proton. Therefore, there is less attraction between the nucleus and the valence shell. So it's easier to remove the electron. So less attraction between nucleus and valence electrons. So it requires less energy to remove the electron. All right, now we have sodium, sodium ion. Which one would have the greater ionization energy? Sodium's electron configuration is 281. It has an ionization energy of 496 kilojoules per mole. The sodium ion would only be 28, and we don't have its ionization energy listed, so we have to think about what we know about our structure of the atom. Sodium ion would have a much higher ionization energy because we have 11 protons in both cases, but you would be taking from an inner electron versus a valence electron. So there's going to be more attraction between an electron in the second shell in the nucleus than there would be between an electron in the third shell and the nucleus. So since the second shell electrons would be closer to the nucleus, there would be more attraction between the nucleus and the electrons. So that would be our explanation. So it would be greater attraction. So there would be a greater attraction between the nucleus and electrons in the second shell than electrons in the third shell.